Okay, you guys, let's do this example now. Let's find the extrema using Lagrange multipliers. The function is f of xy equals x squared, y squared, z squared. The constraint is actually a sphere. So what we're saying here is the only x, y, and z values you're allowed to plug in to f lie on the sphere. That's the restricted domain. So, I mean, if it helps, you can think of g as x squared plus y squared plus z squared minus 1 equals 0. You can think of this as a particular level surface of g, but it really is the left-hand side that we call g of x, y, z. Okay, so what we need to do is the method of Lagrange multipliers, which says, hey, find del f, find lambda del g, set them equal, solve the system, and those are your critical points. It's actually quite simple to state. To actually do, that can be another story, as you might imagine. But it's a simple idea. So let's find del f. What is del f going to equal here? So partial with respect to x times I, what's that?
2x times y squared times z squared.
I, there we go. And then plus 2x squared y z squared j, right? And then plus 2x squared y squared z to the first power. Okay. Does everybody agree that that's del f? Okay, let's find del g. What is del g? Again, you can think of this guy as g. So what do you get there? What's the partial with respect to x? 2. So 2xi plus partial with respect to y, 2y times j, plus partial with respect to z, 2z, k. And then we really want lambda del g, and I like putting in the lambda afterwards. Doesn't really matter when. And then what do I do with each component? Set them equal, right? Lambda del g equals del f, which means their components are equal, and that by setting the corresponding components equal, that's how we get our system of equations that gives us our critical points. So we get the equations 2x y squared z squared equals 2 lambda x. Would you agree with that statement? Okay. And then what's the next one? 2x squared y z squared. 2x squared y z squared equals what?
2 lambda y.
There you go. And then what's the final equation?
2x squared y squared z equals 2 lambda z.
2 lambda z. Yes. And then there's one other equation, the constraint equation. You can either write x squared plus y squared plus z squared minus 1 equals 0, or just take the given equation. I'll take the given. X squared plus y squared plus z squared equals 1. It's the unit sphere, right? Does everybody see where that comes from? So now how many equations do we have? 1, 2, 3, and 4. Which is good because we have 4 unknowns, right? If we want to solve for all the unknowns, we need 4 equations. All right, well, there's more than one way to solve these equations. Hopefully it's obvious. If you look at the function, it's always non-negative, right? Because the function is x squared times y squared times z squared, right? So what's the minimum value going to be? Anytime either x, y, or z is 0, then you've got your minimum. Okay? So I'll make a note of that. I mean, that's just an observation. We're not really using Lagrange multipliers to observe that. Note when x equals 0, and it really is or y equals 0, or z equals 0, when one of them equals 0, which means there's an infinite number of critical points, right? Because the other two don't have to equal 0. I'll say, comma, f equals 0, which is the minimum. Now, when x equals 0, for instance, y and z can't be anything, right? They can't be anything you want them to be. They do have to add together, when you square them, they do have to add together to make 1, right? They do have to satisfy the constraint curve. But of course, there's an infinite number of numbers that do that, so I can't list them all. So I just make this note, which is, it really is an absolute minimum on the constraint, right? And I suppose it's the absolute minimum on the entire function, too. So the only interesting thing happens when none of them are 0, right? So assume that x, y, z, none of them equals 0, which gives us a little bit of leverage here. Take a look. Can't I look at equation 1 then and solve it for lambda? I have no fear of dividing by x now because I'm assuming x is not 0, in other words. In fact, couldn't I divide it by 2x? Well, do I want to divide it by x or lambda? Let's solve for lambda. Yeah, let's solve for lambda like I was gonna. And so I have no fear of dividing by x because I know it's not 0. So, but let's divide by 2 lambda to get rid of those 2's as well. And what do I end up with? So we're dividing by 2x, so we end up with just lambda equals
y squared z squared.
Y squared z squared. Everybody agree with that statement? Could I do something similar from the second equation? Could I solve that for lambda? Couldn't I divide by 2y since y is not 0? We don't have to worry about division by 0 here. So what would lambda equal? If you divide out the y, what do you get?
X squared z squared.
X squared z squared. And then finally, I can get lambda from the third equation if I divide both sides by 2z.
X squared y squared.
X squared y squared. So I'll say this. From
you wrote x squared z squared.
yeah, I should have said x squared y squared. That's what I meant to say. Yep. Okay. So I can say this from the first 3 equations. From equation 1, equation 2, and equation 3, let me put down the equivalents. Okay, y squared z squared equals x squared z squared equals x squared y squared. Does everybody agree with that statement? Okay. If the first 2 equations are true, and again, we're not allowing the variables to be 0, and that's the only time you're allowed to divide by variables when you know they're not 0, right? What can you say about y squared and x squared? You can say that y squared equals x squared, and then from the second grouping of equations, the last 2, I should say, what do you know? What could you divide out? The x squared, so that means y squared equals z squared. So, okay, so the point is that y squared equals x squared equals z squared. Does everybody see that? Now, it didn't go this smoothly the first time I saw this problem. I had to figure this method out. But now that we know that, how can we go back up and look at equation 4. How can we use this result that x squared, y squared, and z squared are all equal? I could change the y squared and the z squared to x squared, couldn't I? And then I'll have 3x squared equals 1. Okay, so then let me say this. From 4, I know that x squared plus x squared plus x squared, in other words, replacing y squared and z squared with x squared, is equal to 1. X squared plus x squared equals 1, which means 3x squared equals 1, which means x equals what? Plus or minus 1 over root 3? Would you buy that? Yeah? No complaints? Okay. So what does that mean about y or z? I think there's a potential problem here with the way you conceptualize the critical points. So for instance, if you wrote the critical points like this, I don't recommend doing this, so I'm going to erase this in a second. So you might think since x squared, y squared, and z squared are equal, that the critical points all look like this, and you could write them in 1, even though there's more than one, right? However, this notation won't work here. Why? Is it clear as to what I mean? Why is it not clear? Because I would think, just reading this notation, I would think, oh, either all the positive coordinates work or all the negatives work. But is that going to be true? No. No, I mean, all we know is that y squared equals x squared equals z squared. So, I mean, yeah, these are two possibilities, right? Either plus, all plus coordinates or all minus, but couldn't you mix and match the plus or minus all you want? So how many actual critical points are there because of the plus or minuses? Well, I don't know how much probability you've had, but if there's m ways to do one thing and n ways to do another thing, there's m times n ways to do both things, right? As long as they don't interfere with each other. So there's actually 2 points you could put here, the plus or the minus, 1 over root 3. 2 you could put here, 2 you could put here, 2 times 2 times 2, there's 8 critical points. So, okay, so it doesn't work. In other words, all the different combinations of pluses and minuses, 1 over root 3, are in fair play here. So how do we write it so that it makes sense? Well, okay, we could just start with plus or minus 1 over root 3, right? And then I suppose if we start with that, then we could have, I don't know, 1 over root 3 for y and 1 over root 3 for z. But then what other possibilities are there? Well, let's stick with the plus or minus 1 over root 3 in front. I suppose we could have y, the y coordinate positive, right? And then the z coordinate negative. Would you buy that? What's another possibility? Let me move this over. What's another possibility? Well, again, I'll stick with the plus or minus 1 over root 3. What haven't I taken into consideration yet? Negative y and say positive z. Now there's actually 6 points here, right? Because of the plus or minus. Does everybody see that on the first coordinate? And then what's another one? Plus or minus 1 over root 3. What haven't I taken into consideration yet? Both y and z negative. And so there's all 8. In as compact a form as I can think of writing them. Okay, so now these are the points you plug in and you see which one's biggest, which one's smallest. Well, the smallest one is going to be when x, y, or z equals 0. So we're just going to look at which one's biggest now, right? In other words, the absolute minimum occurs when x, y, or z equals 0. So we're really only interested in finding the absolute max from these critical points. Okay, so go back up and look at the function. It's x squared times y squared times z squared. Oh, wait. We're going to get the same value, aren't we? No matter which critical point we plug in. Okay. So we can get a little creative here. F of any CP is going to be the same, right? So you see I'm kind of abusing the notation a little bit. These are your critical points. And I'm just, to get it all over with at once, I'm saying f of any CP, what's that going to be? You square the 3 coordinates, what do you get? 1/3 times 1/3 times 1/3, right? Or 1/27. There you go. There's your max, absolute maximum, given the constraint. And of course, we already found the absolute minimum of 0.